AI cloud. It's very different from CPU cloud. So I've grown up with virtualization throughout the larger part of my career, right? The funny thing is that running an AI cloud is the actual opposite of running virtualization. In virtualization, you take a single compute instance and chop it into small pieces, and you create what is called VMs. To run an AI cloud, you take multiple compute units and you get them to work as one. So it's more akin to what the old world knows as HPC, but you need the flexibility of what cloud offered. And that's what we're hoping to build. There are a very few vendors globally that have managed to pull this off. I think we're the only ones in India that have really managed to build a homegrown orchestration stack. And some of the challenges, some of the things that we are still working through, Mohan will talk about. With that, Mohan, all yours.
Yeah, thanks. Thanks, Dave. Thank you very much. Hi, everyone. My name is Mohan Raj Davala. So I'm actually pre-sales manager. I'm part of Neysa's team, right? So in today's presentation, what we are actually going to say is, first we'll start with what is GPU architecture, and I'll actually touch upon AMD MI300, and I'll also touch upon like NVIDIA B300, and we'll give the comparison. And I know some of your workloads right now that what you are running is actually on the NVIDIA, so that I'll also talk about how we can go about from NVIDIA to AMD migration, and what are some of the equivalent stack what we see in NVIDIA and what we are seeing in AMD. And then we know we have the GPUs and it is actually very good at doing the job of the parallel operations and everything. But why exactly we need AI clusters? What do we mean by AI clusters at all? So that part we'll actually talk about it. What is AI clusters? Why we need AI clusters? And how we go about building the AI clusters itself? And what is the problems that we are actually facing when we are building actual AI clusters that is meant for training and the large fine tuning and then large scale inferencing as well? And with that said, AI clusters, we also need to touch upon what is GPU to GPU communication. I'll touch upon that. And I'll talk about each node will come with 8 GPUs. But when you go for the large scale inferencing and the training, you also need node to node communication also. So I'll talk about that node to node communication also. And I'll touch upon the existing setup of what's bits right now have, and how we can go about the Slurm convergence, and what is our recommended setup that we are actually looking at. And I'll give you a short walkthrough of our demo platform, so that you know that how exactly we can spin up the VM-based GPUs and start consuming it. And then I'll talk about the trends and evolution of GPUs and LLMs from here onwards, and that's the conclusion, right? So without further ado, let's get started with GPU architecture. So if you look at the GPU, the main 4 things that what we need is, the first one is the memory capacity, so that you can able to dump your entire model weights. For example, let's take example of 70 billion model for the next few slides. So let's say you want to actually consume that 70 billion model and you want to use it for the inferencing. So you need to actually put it in your memory capacity, and that HBM memory should be able to hold that one, right? So 70 billion model with the BF16, by just model weights itself, it needs 150 GB of HBM VRAM memory. One single GPU of H100 cannot be able to hold it, which means you need second GPU as well. That's the problem number 1, right? Second one is the memory bandwidth. What is the memory bandwidth is, even though you put all your models into the memory, you need a bandwidth that can able to fetch the model weights from HBM to your CUDA core, so that it can able to do the matrix multiplication, right? So it's the communication, the bandwidth communication between the HBM to the CUDA core's compute itself to perform this tensor core's matrix multiplication. And the third one is, of course, the compute precision. Right now, as we are speaking, if you are talking about the H100 and H200, you need to see from the ground level what is the matrix multiplication that GPU can able to handle it. For example, if you look at A100, it can able to do only FP16 and FP32. That's why you never see that FP8 matrix multiplication was not there in A100. But whatever you do it actually done from the PyTorch level, not from the GPU level itself. And then H100 and H200 came in picture. By native, it starts supporting FP8 matrix multiplication also, right? If you look at the B300s, that's what I'm going to talk about in the upcoming slides. B300s by natively, it supports FP4 matrix multiplication as well, right? So this compute precision is very important. So on each layer, what is the quantization that you're going to set, so that according to that, your HBM memory is going to consume. That actually gets decided by the memory capacity. And these three things are one part. The fourth is the another level, right? So the interconnection between one node to another node. So we are talking about one node. Each node will come with 8 GPUs. What if your model cannot able to fit it in a single node itself? Let's take an example of OpenWeight's model GLM 5.1, which comes with 754 billion parameters. If you put like FP16, that itself is required like 1.5 terabytes of memory. It is what it is required. And you cannot actually put it in one single H100, because one single H100 comes with what, 8 by 8, like 640 GB of node capacity, which means you need 2.5 times of H100 nodes. And then you need to interconnect with each other so that it can able to serve it. So that's where it comes, the picture of like what is the interconnection between one node to another node, and what is the interconnection between GPU to GPU, whether it can able to cope up with your inference speed or the training that what you actually require. So those are the things that I'm going to talk about in the upcoming slides. So with this 4 things in mind, let's go ahead, right? So let's assume that same model, which is Llama 70 billion model, that you want to actually put it. The traditional way of actually serving this 70 billion model is split it across multiple GPUs and put the tensor parallelism into how many GPUs that you actually wanted. For example, let's say you have 8 GPUs that are there in your server. You put the tensor parallelism TP equal to 8, and then this model weights will be actually split across each GPU, and then it get actually served. This is as a workaround we do it, right? But still, GPU to GPU communication will actually comes with a communication overhead. What do I mean by communication overhead is, every time GPU does the calculation and comes up with a gradient, matrix multiplication, even the second GPU also does the calculation and it comes with a gradient. Both needs to actually put it in sync. That's what we call it as collectives. I'll talk about in the upcoming slides. This collectives needs to happen between every single GPU to GPU communication and node to node communication, right? So how AMD is actually solving it? So AMD MI300, which is equivalent of NVIDIA's H100 and H200, it comes with, initially it comes with a higher bandwidth, 192 GB of high bandwidth that you are actually getting. So in a node, you can able to easily fit in that large scale models also. And it also comes with the memory bandwidth of 5.3 terabytes per second. So I'll just give you some ballpark figure number. Same model, Llama 70 billion model, let's take. Llama 70 billion has total transformer blocks is 80 transformer blocks will be there, okay? Inside each transformer block, we all know that it comes with first feed-forward neural network, and it also comes with this self-attention layers, whatever, how many layers that you're actually keeping it, each transformer block, and then there is some normalization layer, right? Now, for each time you have to go for forward pass and backward pass per epoch, you need to actually do the sync between one GPU to another GPU. We call it as NCCL communication. Collectives communication will happen. One feed forward network, forward and backward, two NCCL calls will be made. And the self-attention, forward and backward, again, another 2 calls will be made. So one transformer block will have 4 NCCL calls of all radios, okay? Now I said Llama 70 billion comes with 80 transformer blocks, 4 multiplied by 80, which is 320 forward and backward of the NCCL calls needs to make, correct? Let's assume that each NCCL call is taking 1 second. For now, let's assume that. So which means 320 seconds it is taking, which means 5 minutes. So the same, if I have that 5.3 terabytes of seconds versus whatever H100, which is coming up with 3.2 terabytes of seconds, I can able to run it the same transformer blocks for one epoch. I can able to finish it within 3 minutes in AMD. But if you go for the NVIDIA's H100 or H200, it will take 5.2 to 5.3 minutes. So for in a epoch, one epoch, in a training, you can actually save around like 40% of the NCCL communication overhead can be saved. So that's the difference we are saying between AMD's MI300 and the H100, right? And of course,
so basically, all these numbers are
within a node, correct. Right now we are talking these numbers, memory bandwidth and memory capacity is within a node within GPU.
So model fits on a single GPU. If it's across nodes, then also it has no problem.
I'll take a stab at thing. So one of the things that you should remember, and you're right, if a model fits on a single GPU, absolutely none of this matters, right? Only IO matters, right? The downside about the world we live in today is that the average size of models has been consistently increasing for the last 2 years. 70 was considered a huge model some time back. Kimi-K 2.6 released at 1.6 trillion parameters.
Yeah, correct.
Right. I know a lab that is working on a model that is 2.3 trillion parameters. It's coming. I'm assuming about October. Right. So the pace at which models are becoming bigger is significant, and that's how they're driving what they call intelligence. I have opinions on that as well, but that's how they're driving what they call intelligence. On the other hand, you're right. There's another set of folks that are working on getting the model smaller. The good enough ideology, right? The good enough ideology is being put into cars. So if you go and ask your car to roll down windows nowadays, a lot of cars do that. All of that is as small language models. Your transcription that happens on your phone is a small language model. So there is a divergence. There is the small models that are becoming smaller and smaller, and those are typically specific use cases. And the general intelligence models are becoming bigger and bigger. And where it's going, it is definitely not one single node. Yeah.
And this references is actually from the inferencing perspective. But if you look at even the small language model, you want to do the training. Let's say that's again second part of the story, right? First part of the story is inference. If you can put it in GPU, that's fine. And if you have to go for the bigger one for the GPU to GPU, but for the training, you cannot, even the small language model, you cannot actually fit it in one single GPU, because your training first starts with weights, and it will be coming with FP32. And your training will have a RM optimizer that will actually be another BF16 or FP32, and it comes with the master copy, another FP32. So which means you have to do it at the accuracy level to capture the proper gradient with the FP32 or BF16. Otherwise, you cannot actually capture the gradient at the FP4 or FP8 level. So which means, in a way, even if you want to do the training, you need multiple GPUs or the multiple nodes where the communication does matter. That's the whole point. Yeah. 30. Yeah. Yes. We have actually tested it also. We did it with H100. Single GPU is enough to fit it in, but it depends on, again, for the inferencing. I believe your question is on inferencing. No chance.
So how much you typically need a start of a training run? Just to start it up, you need about 5 times the target.
So I just want to know actual numbers. So the demand and
okay, yeah. So you're confusing two things. When you train, your gates, when you're inferencing, your gate is memory, your gate is IO. Yeah. When you train, your gate is not memory. Your gate is typically compute. Because you'll saturate compute, and the other gate is how far to pull from storage. Right? Yes. Those are your gates. Memory stops becoming a gate. But the problem, and which is why when you train, You don't do it on one GPU, you do it on 200 GPUs. That way you can pull more data parallelly. You can shard the job more accurately, and you can leave more data in memory so that you can run more iterations parallel.
So on this, I have a slide. One.
Oh, okay. I think you should.
Okay. I have an upcoming slide for this. When you actually pick a model for the training, what are the weights that it actually comes with, and it gives the ballpark figure number in the upcoming slide. But yeah, as Zeev mentioned, that's the first starting point you should.
What we've seen, right? And I've not seen a 70 billion parameter model being trained, unfortunately. The largest model I've seen being trained is 17 billion parameters. And the least you can do that on is about 16 nodes. 16 into 8 GPUs. So 7 billion parameters. If you want to do it, each run was about 2 weeks for that.
I'm not sure if you will include this, but what about the fine-tuning requirements here?
Fine-tuning is much less.
Yeah, fine-tuning is much lesser, but I don't have specific slide for that. But I mean, I have only training and inference part. But if you talk about the fine-tuning, I think we can remove some of the I'll talk in the upcoming slides. Basically, the first few steps, which is the model weights and that master copy, is not required in fine-tuning. All you need is just QLoRa or LoRa adapters, and then you just put it as adapter on top of the optimizer. Right, so that actually will actually cut down the cost of like what 2 to 3 times, but still it is more than inference. Yeah, right. So on the right hand side, that is actually the chassis detail of the AMD. Just for your information, on the left side, you can see the reason this petaflops for each of the floating point, which is 8, 16, and 32. It depends. It does matter when it comes to where exactly. If it is like FP8. Then most of the time we'll inference with FP8 or FP4 we have to go with, like B300 FP4 by native it supports. And TF32 and FP16 is actually for training or the fine-tuning part. That's what we actually use it for. Right. So this is the head-to-head comparison between AMD MI300 and H100 and H200s. So we already discussed in the last slide. So the main part that we want to actually bring up here is look at the HBM capacity, where you can able to bring in a big model and you can able to put it in a single node itself. That's a huge advantage, because we'll talk about the node to node communication also. What is the difficulties that you will be facing when you're going for node to node communication? So it's always better putting in a model, putting in a single node itself, and if it can able to run it in a single node, that's actually always preferable. So in such case, the HBM capacity is what we want, and also the memory bandwidth catering to the high HBM capacity. And then, of course, the whatever BF16 that there are 2 types of vectors you will be seeing. One is the sparse, the other one is the dense. So it's up to you to decide. So most of the time in the inferencing, we use sparse BF16. Sparse, basically the embedding will have like zeros, a lot of zeros there. But in your training case, you don't actually zero. You actually try to use whatever the accuracy, because you try to push the accuracy, even the slightest gradient. I'll tell you one example. What is the difference between a word man and a guy in an embedding matrix? So as a human, I know that both are actually going to be the same. But when you're training a large language model, there is a small slightest deviation will be there. The cosine matrix similarity will be like mostly same between these 2 embedding matrix. So there will be like only 2 values are actually changing. What if that actually values changes in the FP16 at the end of that exponential, and if you have FP8, then you will be losing those contexts. So this language model will never be able to learn what is the difference between man and guy if you actually train it at the FP8 itself. So that's the whole point. So either that's the reason you actually go with BF16 and or FP32s when it comes to the training, right? Okay. So this is the GPU to GPU communication. So in NVIDIA, each GPU is actually connected with other GPU through the NV switch. So we call it as an NV link, and there is an NV switch which is connected in 8 GPUs, and it is all interlinked together, and we call it as aggregated a bandwidth, which is 900 Gbps. But one slight difference in AMD would be like this is all-to-all communication. It's a mesh topology. So at any point of the time, if you see, each GPU will have like 7 connections to other GPUs, and each link will come with like 120 GB per second. So if you multiplied 128 GB multiplied by 7, you will be actually getting 896 GB. So which means almost like NVIDIA's NVLink switch, 900 GB per second. So this is for GPU to GPU communication. So the one difference that also another advantage in the AMD is at any point of the time, let's say the worst case scenario, your GPUs are down. Bisectionally, if you divide this mesh topology, at any point of the time, you will have 4 GPUs are always up and running, and which will give more, which will give like 450 GB per second, more than whatever NVIDIA's NV switch is actually giving, right? So that's the primary difference between GPU to GPU communication difference between AMD and NVIDIA. And this is the software stack for AMD. I mean, till 2025, of course, AMD also doesn't have the complete whole stack that it can able to support right from the CUDA layer, which is equivalent to NVIDIA's. But I think AMD also figured out, and they have the ROCm. I think it's pretty stable, and you can have like most of the kernels, which is the Triton kernels, or some of the kernels like what is it? Exactly, Megatron kernels. So these are the kernels that you can actually just download it from the ROCm fork GitHub itself. But the idea here is to give you the feel of what is exactly that NVIDIA is actually running on, and what exactly the equivalent in the AMD. So I want to actually touch upon 2 things mainly. So there is, if you look at the CUDA and CUDA toolkit, everyone thinks that the word CUDA itself is actually the ROCm stack, but it is not. Basically, CUDA toolkit is actually equivalent to the ROCm stack. It's actually the base libraries which actually run. When you talk about the CUDA, it is actually the API layer which sits on the CUDA toolkit for NVIDIA. So similar in AMD is there will be a ROCm stack. On top of that, there is a HIP layer, which is also again another wrapper. So what you do is, anything that you have that CUDA kernels or anything that you already have it with NVIDIA, you should be able to find it out in the ROCm GitHub fork. But if it is not available, then you can, AMD is also giving a HIP CLang and HIP Perl. So there are 2 tools are available that automatically you just need to actually upload your custom kernel, and it automatically convert that CUDA kernels into the AMD's dependent libraries, which is the HIP libraries. We'll see in the next slide how it will be done. So I'm coming there.
If you've played around with this 6 months ago versus today, there have been drastic changes. AMD is improving quite significantly month over month. That said, it's not as straightforward.
Yeah.
Right? It's complicated. If you're not willing to put the time into getting AMD to work, don't. Right? But raw performance, AMD has traditionally been better, chip to chip. Price performance, AMD has always been better. Right?
But what I'm also trying to sort of think in the background. What I'm also trying to think in the background is what are those, like, what are the differences between the NVIDIA and AMD architecture which will allow me to change the underlying LLM architecture or deep learning architecture itself? Like, can I do better, say, graph learning, or, slightly?
If your target is to be working at that layer, my bet is that AMD will be better.
Yeah. So
plus they will be more willing to open up and help.
Okay.
NVIDIA is typically not.
So one of the things we are working on is we wanted to build on-the-fly graphs on the GPU, for which I found that existing libraries are pretty bad because they cannot actually construct the graphs, and I might as well do it on a CPU. So I was thinking, does it help or not. As of now, I don't know.
What are the libraries that you are actually using today? I mean, if you can give the example, like, are you talking about the graphs, CUDA graphs? Is what you are talking, or
No, not
or
CUDA, not CUDA graphs.
Okay.
So these are, so think of some random embeddings in the
okay,
space. I want to construct, let's say for the sake of simplicity, a minimum spanning tree
okay,
on that. The problem with minimum spanning tree is it's not as easily parallelizable as, say, a matrix multiplication.
right,
So the way you do that is use some randomization tricks along with, trying to sort of collate a lot of, like, do a.
But standard libraries don't exist for it at this point.
Standard libraries don't exist for it. For the CUDA, for the proof of concept level at which we work, I wrote a kernel.
Yeah.
And the way I did it is I tried actually doing the CUDA, it never worked. So finally I wrote the kernel in PyTorch and gave it to that. And it worked almost, like, the speed was all, I might have as well done it on a CPU.
Yeah, that's not scalable after that.
It's not scalable after that. So I guess my question is, say if I have to do this on AMD, how much should I struggle? How much should I know?
See,
What you're trying to do is a struggle wherever you do it.
Okay.
Right? The question is, which system will be more amenable to going and opening up base level code to be able to go and do that? And my bet would be AMD. I'm not, it's not an answer. I don't know because I've not tried. Right?
Okay.
But I can go do some digging and check. Write down, send me a note. I will talk to both of them and figure it out.
Okay. So I guess other thing which I always hated about CUDA was the documentation is bad. How is AMD documentation? I've never actually tried it.
The problem and the reason you think documentation is bad is because there are new versions coming so fast that documentation is not able to keep up.
Yes.
Right? That's not a problem that's going to go away in the world of AI.
Yeah, but at least, I mean, if I do the problem with CUDA was so they had this QGraph library apparently, and I thought that fine, maybe I can use it. I tried loading it, and then it says that no, your driver is not compatible with it.
Correct. Because nobody updated it.
Nobody updated the underlying documentation.
Yeah.
My question is, how much of such things actually happen in the AMD?
Yeah, I said you're not. That problem exists everywhere.
So even I tell you, for the Gemma 31 billion model that you already bring up, I tried to test it. The same problem, driver is not existed, and it was actually keep crashing. I'm not sure if you have tested. So if you update the driver, it will actually not actually in line with VLLM and the SGLang for the inferencing perspective, which means either driver is not exist, or even if you modify something based on some of the GitHub fixes that open source community is doing, I go and fix that inference side, VLLM also is not catching up at the same pace. So the thing is, it is always be there. It's always a catch-up game.
Yeah. Okay. You're talking at one level. I'm saying every layer that you're talking about, and there are a bunch of layers that are not listed here as well, right? Firmware of the NIC card, firmware of the which firmware is on the thing. They're building compatibility across the entire stack is today an art form. Right? And I'm not kidding, it is.
I agree.
Right? Because no documentation exists anywhere. In the old world, Linux, I could go put it on some forum and get an answer. It doesn't exist today. There is no answer. You've got to go figure it out. And the amount of times we've gone and rewritten firmware drivers, I have team to do that. Yeah. Right? Why? Because otherwise my system doesn't work efficiently.
But I mean, so that those details become pretty important for people. I mean, for the researchers, especially. I mean, I don't work on the high performance one, but I have a few colleagues who do.
See, unfortunately, I can't do across the stack. I can go and say that I will do all the way till OS, right? And that's why my line draws. Even that, starting from firmware to NIC card to network switch to SFP flash has resulted in problems for me, right? So each one of those and getting those to work well is a 60-man army that is good at what they do. Above that, unfortunately, I can advise, but I can't do.
No, I mean, yeah. So basically, I just need the information.
Yeah. So yeah,
So that
our guys are playing around with it always, because of which they'll be able to say, "Hey, I think you should go down this path."
Okay.
But that is not a guarantee.
So you guys provide some forum or something?
Yeah. So typically we create a Slack channel with everybody, and I'm on many of them. The kind of stuff that goes on over there is phenomenal.
Okay.
This is how we also learn, by the way. Which is,
I mean, I definitely, as of, I don't remember any of this from my end. So, okay, so you're saying, so basically to summarize, you're saying that AMD documentation is as bad as...
Nobody's documentation is good.
Yes,
by the way,
great.
I've gone, and these are 2 GPUs. We are evaluating others that are coming and building TPUs, other GPUs. There's a Korean company that has built a fairly good product, 0 documentation.
Okay.
Right? Live with it. And by the way, they're all smart people. You get on call with them, they all know it, but there's no documentation.
Okay. Okay.
Yeah.
Thanks.
So with that, so you also mentioned that you have actually written the custom CUDA kernel. Let's assume that you have the custom kernel. That's where actually the main bottleneck comes between NVIDIA to AMD. So that's the manual work. So wherever you see the drop-in, all of these things are available. It's mostly available in your ROCm fork GitHub. You should be able to get these drop-in details where you see that manual thing. So this is the procedure that you have to convert it. If you're good at C language, C, C++, you can use Hippify CLang tool. You can actually provide your CUDA driver, and then Hippify will actually tell you first, the scan step will actually tell you how many kernel object calls that you are actually making that can be exactly converted into the Hippify objects. That's what you see is as replaced, is 47. And you see there are someone is warning, which is 3, but exact object calls are actually not available. Then it will raise a warning, and then you should be actually doing that manually, sitting and fixing that in the C++, or you can use Hippify Perl. You can use the Perl language and you can do it. And once you're happy with all of them are comfortable and everything, you see that it can be replaced with CUDA, then you convert it and then you compile it with the PyTorch. So this is the three-step procedure for converting your custom kernels from your CUDA to Hippify, like to the AMD.
After this process,
they are actually pretty much the same, because once it is done, this is actually in the Hippify, then it actually goes into the LLM, right? I mean, it should be the same. Okay, so that's actually on the AMD one. So let's jump gears on the B300 right now. So if you look at the B300, what is the next version that we are actually looking at from H200 is, okay, there are on the left, on the right side, you can see these are all the chassis details, but the main important thing is again the HBM3. So it's actually HBM3 enhanced, where it comes, each GPU will actually come with 288 GB of VRAM. And you should be able to use the bigger models also here. And it comes with almost 2 times of the HBM bandwidth, which means whatever you were able to do it in H100, you should be able to do it like 2.5 times of the bandwidth is actually more for B300 in this case. And also it supports, native support is for FP4, which means in H100 and H200, there is no matrix multiplication at the FP4 level. But you may actually tell that, hey, I'm using FP4, but it works, like AWQ Marlin is there and I can able to use it. But that's actually not from the GPU level. Whatever you do it on the FP4 in the H100, it actually does on the software level, PyTorch level. And then it goes to, so there is a little bit of lag will be there between native support of the driver chip side and the software side. But B300 comes with a native support in the chip itself. So by default, it comes with NVFP4 and MXFP4 also. So that's tensor core matrix multiplication you can do. So other than that, NVLink 5, So if you look at GPU to GPU communication in H100 and H200, it's 900 gigabytes per second. Here it is again twice, which means whatever the collectives that you are doing, all reduce and everything, it will be just it will double here in this case, like because it's a 1.8 terabytes per second is the GPU to GPU communication here, right? And okay. The one thing, the major difference is node to node we haven't actually touched upon, but we'll touch in the next upcoming slides. That is actually 400 Gbps of the node to node communication, but B300 also comes with 400 and 800 Gbps also.
See, one of the things that I want everyone to keep in mind that while 800 exists, it is today Rolls-Royce, right? 800 Gbps networks exist. An 800 Gbps port is about 6 times the cost of a 400 Gbps port. So it's about three times the price per Gbps. So unless you absolutely need it, don't. Right? The same applies to the Grace Blackwell. The Grace is the ARM version of the Blackwell, right? So you've got AMD CPU, Blackwell GPU, Intel CPU, Blackwell GPU, Grace, which is the ARM CPU, Blackwell GPU. Grace Blackwell has advantages, but it is again, it comes only as a 72 GPU box, 72 GPUs on a box, not partitionable, not segregatable, and costs about 30% more per GPU. So if you're not going to be able to use it, don't take it. So and it's, by the way, it's not impossible to use. I'm very, very tempted. Very, very, very tempted. As a CSP, I am very tempted. But I've not been able to justify the cost delta.
Right. But from the NCCL perspective, the software stack is going to be the more or less similar between H100 and H200 and B300. So it's just a backward compatibility also. So whatever you do it with the CUDA kernels and everything, so that actually can be migrated to B300's compatibility, right? So this is on the architecture perspective, but we'll touch upon B300 training and inference in the upcoming slides. So going ahead with the L4. So, okay, we are talking about the bigger GPUs, and then we suddenly shift our gears to the smaller ones, because I also want to give the numbers on, because you also have the requirement that the upcoming phases of your AI journey, that you're expanding your campus and you actually wanted to serve a number of students as well as, right? So for that, L4 is the one that the good proposition. And these are the numbers that whatever the numbers you are actually saying. So these are numbers that we are actually doing it with one of the private food delivery company and also some of the bigger education universities in India. So these are the real numbers, how they are actually consuming it today, right? So if you look at, and these are all actually deployed in L4. So if you look at Llama 3.2, 1 billion instruct. So this is the input and the output tokens is the size, and you can able to support number of concurrent users, 50 users per L4. Right, and similarly for the 7 billion model, it's a per L4 is a 12 users, and based on our previous discussion with you guys, then we thought, okay, for 1,000 users, what is the approximate? Again, these numbers are actually tend to change, depends on how you are going to consume the input tokens, output tokens, all of these things. But just to give you the ballpark figure number, how many L4s it really makes sense if I have to cater to 1,000 users, and what are the concurrency it would be, and what is the headroom that I have if based on the peak or based on my average utilization of my GPUs, right? So this is for the L4. So I'll give you a short demo in the upcoming session for L4. This one. Okay. So I'll just maybe so I'll tell you this one. So total users. So this is 60 by L4 capacity for 1,000 users. Total users is 1,000, and peak concurrency, I'm assuming at any point of the time out of 1,000, 250 users per second is going to use it.
You continue.
Yeah, per second, 250 users are going to use your entire.
Oops.
I think it's already in
No, but
presentation.
we should. No, you continue,
Okay,
man.
sorry. The L4 cards, total L4 cards is like 60. And there are two models that we took. One is the 7 billion, which is in the AWQ, which is the FP4, essentially in the inferencing, and 1 billion, which is in the FP8, right? So what is the concurrency per L4 for this per model is actually 12 concurrency and 50 concurrency, depends on the tokens that we took, input tokens, right? And what is the full fleet capacity? 60 multiplied by Quen 7 billion if you take this one. So this one, for 60 inference in your entire fleet, at any point of the time, 720 users can actually access that GPUs per second. Even actually, it's like considering like, yeah, concurrently, I'm saying like per second concurrency. And if you talk about the 1 billion, so this is actually from a private food delivery company, as I said, right? So they are actually 3,000 users can able to access it per second for that particular region. That's their requirement. So this is what it is. And the headroom that you can see, I'm taking peak concurrency. Let's assume that at any point of the time, let's assume 250 users is going to be your assumption. Then what is the headroom that I have with the expected outcome and your expectation, right? So that's the headroom that we are actually saying. So 2.9 times depends on which model that you are going for and what is your concurrency and other. Right?
Yeah, hello, am I audible?
Yes, sir, you are audible. Yes, please tell me.
Yeah, so great presentation so far. A couple of questions I had. First of all, so I just wanted if you could give a couple of examples where there have been like decent sized or standard projects which have utilized AMD GPUs instead of NVIDIA GPUs. So not in terms of key AMD should theoretically work, but where it is actually being used and working. And I'm particularly asking in terms of the usage of the CUDA alternatives. So more on the software side of it. That was the first question. If you could answer.
Yeah.
Shall I give it a stab?
Please,
okay. So just I didn't get the name. Sorry. Aditya. And I unfortunately can't name the customer because that's still work in progress. But we are in the process of procuring 8,000 AMD GPUs as an inference cluster for one customer. Right. So that's a single cluster running a single model quantized at 6 different ways. Right. Now, at scale, AMD inferencing actually works out more cost effective per token. I'm not going to say better. I'm going to use the word cost effective per token when at scale, right? Simply because the effort that needs to get put in is distributed over many trillion tokens, right? The effort required with every change of model, with every change of VLLM, with every change of firmware is actually quite significant. The team required to go run it is actually much bigger. But in spite of the cost of that bigger team, it actually works out a lot more effective because my net cost per token becomes lower. That's point number one. Second, I have one customer in India who's currently running 2 nodes of an AMD box for fine-tuning a 70B model. It's a fintech, right? They've taken a 70B model and they've fine-tuned a lot of the code that they use, that historic code, into that model, right? So it's normally the choice of AMD versus NVIDIA boils down, and this is from my experience, boils down to the expertise within the team that is buying it and the willingness to go spend the time solving through the problems. Once the problems are solved, AMD always tends to be higher performant.
Agreed. So I would like to add one point, one more customer to that. India's UPI provider, he is actually using AMD, but again, that's actually on the inference side. He himself told that AMD inference, they're running GPT OSS 120B on AMD, and actually, of course, when I say UPI provider, India's largest UPI provider, right? It is actually AMD is killing that when it comes to the inferencing perspective. From the CUDA side, of course, it's everyone. I mean, when it comes to the custom kernels, what are the process, that procedure I mentioned, that we have to go through that. So there's no other alternative way from CUDA to AMD.
Does that answer the question?
Yeah, broadly, I do understand your point. So yeah, it does answer the question to a good extent. A second question which I had, so what we are working on is not more inference, but more on the training side of it. So
Yeah.
training edge models, you know. So our estimation is that we'll require around 8 nodes with 8 GPUs each. So I was interested in understanding how quickly can I get access to them? How long of a run can you allow us? How long does scheduling a job on your platform would take? So the scheduling heuristics and how quickly could we get access to them is one of the points which I would like to hear going forward.
Availability is always there. I always have some GPUs available. 8 nodes, I'll have to go check, and we can come back on. I'll come back on that point.
The another one is the scheduling. So I think for the scheduling part, we actually use the Slurm. We can provide you the Slurm head, and once we actually check on the availability nodes. But again, the thing is, what type of scheduling that actually you want to do? All of these things, if you already have an idea of how your Slurm controller control script looks like, I think it should be pretty straightforward. I think I have a slide also in upcoming slides for the Slurm. One of the slides probably we can discuss there also, but that's actually applicable for both training as well as the fine tuning.
Yeah, just to conclude, so you spent a lot of time on the AMD GPU, and you just briefly skimmed across the NVIDIA B300. So could you just give like a direct one-to-one comparison between the two in like practice?
Okay. So AMD's MI300 is not actually equivalent or comparable to B300. That's the reason that I haven't actually put the comparison. But AMD's 350 is the one actually we have to compare it against B300. That's the point number one. That's why I didn't actually put up the table, because that's not an apple-to-apple comparison. And the second thing is, I touched upon B300, but I think I'm going to revisit the B300 in the next 2 to 3 slides. We talk about the training with B300 and inference with B300, how it looks like for a GLM 754 billion model. I'll touch upon in the next 2 slides. But did it answer your question?
If you could get a little more into the 350 versus B300, if you have like an idea from practice or like what people
okay, so here, and I'll give you a little bit of history. So we bought a bunch of MI300s some time ago, right? I think we have 4 or 5, maybe we have a few nodes left from that purchase as well, right? The H100, H200 we bought, we chose not to buy the B200 because we thought it was a waste of money, price performance wise. The same thought process existed on the MI325. Price versus performance did not match, so we refused to buy it. MI350, we're going to buy 8,000. B300, we're going to buy a whole bunch. We've not decided on the number. So I've not played with the MI350 enough to be able to go answer that question. And the B300 is still fairly new.
Same. That's the reason we touched upon on the high-level specs perspective. But what is the end real-world inferencing or the performance that we are actually seeing? That ballpark figure, just like how you are seeing in the slide, like we are providing it for L4, or I can provide it for even H200 as well. So that level of deep numbers I cannot provide you right now with AMD 350 versus B300. But I think we can always come back to your question. I'll discuss this internally. We can come back. But today, probably I'm not in the good position to answer to that in detail.
Yeah. So just a gentle follow-up. Amongst the nodes you currently have,
Yeah.
which your platform is already purchased, so which nodes do you observe like are the most available or are the most ideal amongst which you currently have and which you have the maximum amount of? Like,
I'll let Zev handle. So, what is the node availability across the platforms? And
L4s, we have a whole bunch. H100s, we have a few. H200s are sold out. MI300s are almost sold out. MI350s are on order and arriving. B300s are a bunch of arrived. They're all sold out. But there's more arriving every couple of weeks. And significant sums. So B300s, I will at least going forward, B300s I will always have. MI350s I will always have. RTX 6Ks I will always have.
yeah, I take 6K as well, correct.
okay, thank you. That answers my question.
Yeah.
Thanks, Aditya. So so even Aditya was actually mentioning about he needs 8 nodes and 8 GPUs in each node, right? So that's where the GPU and communication and node-to-node communication comes, and that's the reason I'm going to put the upcoming slides is why AI clusters. So we all know the difference between CPU and GPU. I'm not going to go through each and every detail. Basically, CPUs are actually can able to do the sequential task, but the complex task. With the ALUs, but GPUs are actually the smaller ALUs. It can able to do either addition or the matrix multiplication, but it can able to do the things faster in a parallel way. So that's the whole difference between CPU and GPU, right? So now let's see the GPU memory bottleneck. Even despite the fact that it can able to do a lot of tasks, where exactly the bottleneck comes. Let's take first example of training. Let's assume that I'm actually taking that open weights, the model who actually have a crown right now. But I think we can discuss the same numbering actually will be the same for Gemma 31 or whatever the number that you actually take it. It's just we need to actually put a ballpark figure number. So let's take an example of 754 billion 5.1 open weight model, right? So the initial parameters, which is the model weights itself, it will take 1.5 TB, assuming that model weights is actually going in the 2 bytes, which is the FP16 or BF16. Right, and then there is a gradients. Gradients will actually go in FP32, and you can do it with BF16 also. There will be master copy. Master copy is always there to update your gradient. So master copy should be always be equal or more bytes in size than gradients. So that's why I took, since gradient is, I took 4 bytes, I'm taking master bytes also. The master parameter is also like 4 bytes. So that is taking another 3 TB. And there is an optimizer state. Let's say you take the Adam optimizer, there will be there will be 2 states in Adam optimizer, M and W. So it depends on that 4 bytes multiplied by 2, which gives like 6 TB. Total is like 13.57 TB of memory. HBM is what you actually require. But right, if you see B300, there is only 288 GB per GPU. So you cannot fit it in one GPU. So you need multiple GPUs in this case. And again, based on the TB, definitely you cannot put it in single node as well. So again, you need to put multiple nodes. So there should be a way that it has to interconnect with each other in such a way that your training is not bottlenecked with the communication and so on. So we'll talk about the collectives part. So the ballpark figure number. So if you see that second point, at this rate, if these are the parameters that you actually use it, then what you require is 6 nodes of 8 GPUs is what you need for this 754 billion parameter that you want to actually train. And I'm not considering still the activations.
Say hello to it. Okay.
Yeah.
That's just to get it running.
Yeah, get it. And still I'm not there at the activations and not the checkpoint buffers. I'm not at there. So that is again another 20 to 30% overhead also you need to add up. I didn't do that calculation, right? So how do we do it? This one, we can able to do it with a data, DP, TP, data tensor parallelism, and also the pipeline parallelism. We can actually use these methods. We'll see it in next slides. So this is the bottleneck problem statement that we are actually facing in the training. So this is the reason we need multiple nodes. When it comes to the inferencing, we know now you may actually tell, hey, B300 suppose by native buys from the chip side itself, it can able to support FP4. I don't need to bother about any other FP16 or BF16 or FP32. So now tell me the data, the same model, and what is the inference it is actually, what is the number of GPUs that it actually takes. So with this context size of the input data, 32K, and I'm assuming that batch size is like FP8, and the weights is I'm taking it like FP4 itself, but the scaling factor and activation will always be like from the FP8 perspective. So I'm actually taking that and put like 410 GB. Still, despite the fact like NVIDIA put a lot of effort into pumping up that single GPU, still you cannot fit it in one single GPU. And we are actually talking about 5.1. There is already 5.2 is upcoming, and it is more than, as Xavier was telling, it is more than that. And Kimi K2 is like 2 times of this parameters. So anyone who wants to do the large scale inferencing also cannot be able to put it in a single GPU. So the whole idea, the problem statement that I'm trying to say here is, for training or the inferencing, the crucial is GPU to GPU communication and the node to node communication. So how do we be able to do it? So there are 3 types of parallelism. I think I'm not going to go for each item. I mean, if you have question, you can let me know. But on the high level, I think you're already aware. You can able to do the data parallelism, chunk the data into the batches divided by number of GPUs that you want to send it to. For example, let's say you have 3,200 images, you have 32 GPUs, divided 3,200 divided by 32, which means each GPU is going to get 100 images per epoch for a batch. It's a mini batch, right, for the data parallelism. And if it is pipeline parallelism, if you can able to put a single layer in a single GPU, then we can actually go for the pipeline parallelism. Or if you want to actually do the tensor parallelism, is like usually we go for tensor parallelism to split that layer across the entire model, and then we actually do the we'll put it in GPU for this. But the difference between pipeline and tensor parallelism here is, let's assume if you actually can go with the pipeline parallelism, there is number of collectives calls, that NCCL call that you make is in pipeline parallelism is actually half of the whatever you see in the tensor parallelism. Because in the tensor parallelism, if you see that layer needs to be like matrix multiplication, and it is a full feed forward and comes back and the backward. So which means 4 NCCL calls needs to be done, considering the transformer block has 1 feed forward and 1 self attention. But in case of pipeline parallelism, you need a better scheduler, because each layer you are processing in a single GPU, unless your first layer is actually processed by GPU 0, the third layer, which can able to process GPU 1, is going to be waiting for your first layer to be done, which means you need a better mechanism. So that's why there are some Megatron, there are some algorithms are there. But of course, there are fancy schedulers you need to actually use it for pipeline parallelism. That's the primary difference between these 3. Okay, now we know model cannot be actually fit in a single GPU. We know that GPU communication is mandatory, and so each GPU, every time that it learns a local gradient, and this GPU to GPU local gradients needs to be shared across the GPUs and nodes to come up with the global gradient. And we know this, and then we update the model. That's the goes the feed forward, and then it comes backward, right? But how? Someone needs to actually do it. I mean, we cannot. I mean, we know that it has to go this way, but how it actually done? So that's where really AI clusters will come in picture, right? So there will be front-end fabric, and this. Right. So there will be a front-end fabric. It's a leaf spine class. And then there is a training nodes. Whatever the nodes that you are actually talking about is actually going to sit in our VPC. So whatever you see, the entire diagram, it's actually there in our AI cluster, whatever we are building in our data center. This is what. And there is a storage nodes, and this storage nodes is actually parallel file system, and it needs to actually give you the details whenever you are asking in the microseconds level. Not even in milliseconds. It has to be like in microseconds. And if you have 2 different clusters, one is for training, one is for inferencing, it's good. So I just put both of them. But if you're focusing only on training nodes, you can assume the training nodes and the storage nodes for now, right? Each training nodes, it will have like a backend network. When I say backend, so I'll talk about like next slides. We'll go each and every phase one by one. So this training nodes will be connected to the backend fabric. So this backend fabric is also again, this is where actually our 400 Gbps of node to node communication happens. And there is a separate storage servers is actually sitting here, right? So these are the numbers, you can see like whatever the gigabytes and everything. So for that node to node communication, we are using Rocky V2. Let's go one by one. So this is the front end network. We have a spine. We'll have like 8 switches of the leaf nodes will be there, and each leaf node will be actually connected to your GPU server. When I say server, it is a node. For example, if Aditya says 8 nodes he wants, and each node will come with like 1 to 3, like 8 GPUs, and each GPU needs to actually connect with each leaf node. And that one we call it as a front end fabric, where your request will be coming from outside to your GPU. Once the request comes from the front end fabric to your GPU, then that's where the rail network comes. This is the NVIDIA specific architecture, but the rail network is actually adopted by even AMD also. What happens is you have a node. First node is that one, and the second node, let's assume this is the second node and third node. These 3 nodes, GPU 0 is connected to each of these nodes through one single rail. And even if you have like 8 nodes, all 8 nodes of the GPU zeros are connected to rail 0. So at any point of the time, if you look at the AI cluster, there will be 8 rails, because each rail is catered to each GPU. And how many nodes are there? Those many connections you will be seeing on the y-axis. So basically, x-axis, you can assume that it is equal to 8 GPUs, right? So this is the rail topology is what we follow, right?
8096 node maximum.
The 8096 nodes. So for example, today Aditya was asking 8 nodes. Tomorrow he comes up with asking, hey, I want 10,000 nodes. Then I cannot actually fit in the remaining 8096 nodes is the maximum rail mesh topology I can able to do. That 8097th node, I cannot actually put it in the single cluster. So I need to find a way to split the cluster and then make it. So I mean, I'm talking about the scale, right? So, so this is the difference between classic and rail. There are other topology designs also there. You would have heard about the dragonfly topology. You would have heard about the fat tree also. So the main point I actually wanted to tell you here is, so you can see the GPUs are there on the bottom level, and if it is all connected to one single leaf as a classic fabric, so it is all actually, all the network is actually fighting towards one single hub. So there is actually, I mean, there is always latency will be there when it comes to the classic, but because it's a shared space, shared hub space. But when it comes to the rail topology, each GPU, which is the 0, you can see follow the colors. For example, red, leaf 0, it has its own dedicated channel, which is connected to the switch to the to your GPUs. So so there will be a low latency when it comes because of the dedicated channel here, right? So that's the difference between classic fabric and then rail optimized fabric. Now let's come to the Neysa AI cluster. Where exactly our technical capabilities come in picture, and what exactly, so even Xavier was actually talking about, I was actually facing a problem with NIC firmware. So those are all the problems, every single space that we actually see. So when it comes to the front end fabric, we have the 25 Gbps of the bandwidth connected to a bare metal. And this is where your bare metal is going to sit inside, either B300 or whatever nodes are. And these nodes are actually communicating with 400 Gbps of the backend fabric. Again, the backend fabric is also another switch. It's a networking switch. This networking switch also needs to be properly connected. And there are 2 types of metrics you need to follow. One is the priority flow control, PFC, and there is another one is called ECM. So these 2 metrics, you need to fine tune it properly so that each node to node, whenever the communication is happening, there is no loss happen between the communication, because whenever the node is talking to another node, there will be NVIDIA will be establishing TCP session. So we will talk about that also. TCP session will be established. So you need to make sure, of course, TCP will do the 3-way handshake, but from the node side, the packets are not dropping, right? Because you have 400 Gbps of the network connectivity between node 1 to node 2, who will actually make sure the packets are not dropping? What if you are running epoch and then there is a loss of packets, and then how do we actually make sure that it is not happening? So that's where the PFC and ECN will come in picture for the fine tuning part. And the storage fabric, we have a PFS system which is connected with a 2 by 100 Gbps, which means by net you will actually get 200 Gbps of the bandwidth capacity that your node can able to access the data from your storage. That's the capacity that you can able to access, and it is all run by Rocky V2, right? So that's on the AI cluster side. Still, we are not yet finished. Like, what are the other problems that we are actually facing in the net? So we'll talk about the GPU to GPU communication also, and then we'll finally discuss the summary. So we know that GPUs have either AMD will come with Infinity Fabric, which is all-to-all connection, or NVIDIA comes with NVLink and NVSwitch. We also know that GPUs always prefer this. We know that rail optimized is done, how the request is actually going from, for example, you order a Slurm, go and do some Slurm job, it goes through the fabric and then hits your GPU, and then it start scheduling those things. Those are actually going the rail optimized. But between one node to another node, some sync needs to be happen. Someone needs to do a manual effort to tell that, okay, this is the first node, this is the second node, and there is a third node that I'm going to add it, and whether this is actually updated or not. Someone has to do it and update the cluster, right? There should be someone. So that's where rank, local rank, and the world size, this come in picture. Okay, so let's assume right now you have 4 nodes, and each node is actually have 8 GPUs. Okay, what happens in the first days? Let's assume right now you have only 2 nodes. Okay, and you have another 2 nodes you want to actually add it. So basically, what you will actually do is, whenever you actually do this connection, you need to define in your Slurm control that who is the master IP for the node. That one, it will assume it as a master IP. For example, the first node for me, this master IP, this is the guy, and he is the master. And once the master is actually set in your Slurm control, and the second node, third node, everything, you will actually define it in your Slurm control script. Once that is done, you will run a torch run in the PyTorch. So what this torch run will actually do is, it will go and assign this ranking. Okay, master node is this guy. So I start the ranking from this node, which starts from rank 0, 1, 2, 3, all the way how many GPUs are connected with this Rocky V2, this InfiniBand platform. And we will do the torch run will actually go and do the assign the ranking. So it starts from 0 to 31. Each local rank, you know that it is always 0 to 7 local rank, right? And the world size is total number of GPUs is 32. Now we know that rank has been assigned by PyTorch, but who is going to again tell that, hey, this is the first node, this is the second node, the third node? Then NCCL sync needs to happen. That will actually happen again. That is actually automatic. So you know, all you need to is just enable a flag in NCCL, and then that will be automatically. The first 2 steps, which is assigning of the master IP in your Slurm control, and then running the torch run to make sure that this is actually in sync. And once that is in sync, you're not actually losing anything on the fabric side. So you remember I showed you the node connected with one link, and make sure that there is no loss happened between one node to another node. That is, we need to make sure with PFC and ECN configs. From the Neysa side, we actually do that. So once that is done, then that's when you actually will see your proper AI cluster is ready for training. Right. So same. Let's take same data. Let's take simple data parallel as a assumption. We just not the tensor or the pipeline. Let's take just data parallel one. Let's assume you have total number of images. You have 3,200, and the total, like, you have 4 nodes. Total GPUs are 32 GPUs. So you will divide that number of images by world size, which is 32 GPUs. Whatever you see here, the world size is 32. And you will actually put it in batches, how many batches that you want. So each batch will be like 100 images, and there is another 100 images. First 100 images, let's say it's go to the GPU 0, and the first local gradient will be calculated. and then there is another local gradient also will be calculated by the GPU1. These two guys needs to actually have a sync, and this needs to be averaged out. So that's where the NCCL comes. I mean, back in like 4-5 years back, we use parameter based reduce a sync between each GPU. For that, actually, the time between each GPU sync communication actually is huge. So, but for now, the modern collective is actually using 6 types of collectors. The one that you're seeing, the all reduce, is what we actually do it from Neysa side. By default, when you are actually getting an AI cluster, we fine tune this RDMA, PFC, all of these fabric things, and also we provide you the all reduce is the NCCL. But it's up to you to change, go ahead and change whatever you want. So what do I mean by that is you can see that collective operations, gather, scatter, all reduce, broadcast, reduce, scatter, and all gather. So these are all different types of collective mechanisms. How exactly each GPU local gradient and other local gradient gets averaged out. So I think the diagram is pretty illustrative. So you can see that all reduce, each GPU have that local gradient A, B, C, D, and we need to actually sum up with A plus B plus C, D. But when it comes to reduce scatter, each GPU will comes with like chunks of that local gradients, multiple local gradients, and it needs to be actually averaged out with the in the row-wise pattern. Yeah, row-wise pattern. And then all gather is actually the sum up with the column-based pattern, right? So the formula, if you use, there are different types of data parallelism is there. One is the DDP, or what I showed you before, and there is a 0 DP data parallelism, and there is a FSDP. I think most probably you would be using the modern FSDP is the one that everyone using. If you go with FSDP, biologically on the software level, FSDP follows this. This is the approach they follow. They don't directly go and do the all reduce. All reduce collective is equal to reduce scatter plus all gather. So first you do the multiple chunks of the local gradients, and then you sum it up with the all gather. That's how you actually get the values. For each GPU will actually arrive at the average gradients, right? Okay. Same thing, like okay, I just simply put A1 plus B1 plus C1 plus D1, but you may have a question. Okay, so I just put like A1 plus B1 plus C1 plus D1, but you may be having, hey, how exactly it's arriving? Like how is this summing up is actually happening? You cannot just say, okay, whatever it is there should be logical communication. Right now we are talking about 4 GPUs. I have like, let's say 8 nodes. 8 multiplied by 8, 64 GPUs. There should be some logical algorithm that should be there that can able to tag each of the GPU's local gradients and map it up, right? So that's where the ring algorithm and then tree algorithms. There are 2 types of algorithms are there. Once you do this, NCCL is actually perform the local gradients and global gradients. But how do you actually map it is actually from the ring topology. Now you can see here, each GPU have a ring connection to the other GPU. This is all in NCCL. A4 is pointed to B4 and B3 is pointed to step by step. So this is how it actually sums up. So A1 plus D1 is actually comes from this D1, the first step, and it goes to the A1 plus D1. And A1 D1 is again followed to another ring topology, which is B1. And this is, so if you go step by step, each and over and over again, this is how the all reduce algorithm actually perform. And this is again still in this first step, which is the reduce reduce scatter. In this first step, GPU 0 is aware of the vector, which is the A3, which is a matrix, the embedding vector. GPU 1 is actually aware of A2. Again, so each GPU knows only one vector. But what I want is it should be sync, complete sync, which means I need to do the ring algorithm again one more time in a way that it can able to share, and then so that each GPU is going to have the same information. Because if I have the different information between one GPU to another GPU, then it is not complete sync. The backward pass gradients will not get updated, right? So this is how the all reduce will actually gets updated. And this is the rings, and there are 2 types of ring and algorithm and double binary. So this is the test actually performed by NVIDIA team. So anytime if you have number of GPUs that is actually less than 96, it doesn't make sense whether you're want to go for rings or the trees. But if you have that number of GPUs are actually scaling up more than 96, you are going for the training, your tree algorithm, you more than you're using ring algorithm. If you use tree algorithm, you'll have a significant amount of latency saving and also the bandwidth saving as well. Right. So yeah. So we have any questions over? Yeah. You have any? Yeah. So yeah. So so this one, right? So these are the problems. So now you see, it's not about I have a money, I just buy a hardware and then put it and I can actually expect it will work. No, it is not that case. The first problem that is the GPU refresh cycle. So every 3-4 years, GPU is gonna change, and it's actually a huge capex burden for you, right? I mean, it is not really for you to make sense. Like every 3 to 4 times, you need to actually make a capex, and then you also need to do all the work that whatever the fine tuning, the fabric changes and everything you need to actually make it. That's the problem number one, which our Neysa, we actually handle it because that's our core business model itself. So the second one is the RDMA and NCCL fine tuning, which means one node is communicating with another node. There is a switch which is sitting, which is not visible to you when you are actually accessing the cluster, but there is a switch which is communicating between the nodes. So someone needs to actually make sure that there is no loss. There is priority flow control is there, which is make sure that your whatever you're actually saying that it is not getting dropped out as a packet. So those are the RDMA fine tuning that we have to do it. If any wrong setting, that will again have a hit of 30 to 50% collectors will be latency will be there. Right. So the third one is the fabric refresh. So you saw that AI cluster is actually based by front-end fabric and the back-end fabric. Both the fabric, someone needs to manage it. It's not directly I just plug and play the cluster itself. So each fabric, the front-end fabric will come up with a different network, which is a leaf spine class, and the back-end fabric is our back-end fabric is a rail mesh. But you may have your own a topology also. But just in case, today we are actually doing rail mesh because we want to cater to the broader audience. But let's say you have your specific use case. Let's say Aditya has specific use case. Hey, I have 8 nodes, but rail mesh is not really good. But as per this paper or something, I see Dragonfly can be better, right? So Neysa, from our side, what we can do is we can also, as a cluster creator, we can actually work with you as a partner, and you have like significant, make sense. Okay, these are the nodes that you want to actually have. When we are creating cluster, we can actually customize that also for you, right? It's not that we always have to go for this one, because we use rail mesh. It's because it's widely acceptable, and it's actually applicable for everyone.
Simply works best for.
Yeah, right, inference. But if you have your own topology that you want to actually modify the AI cluster, then the best possible ways you can, Neysa as a partner, we can actually do that and customize that for you as a AI cluster. That actually comes from the fabric side, from both front and back end. So fourth is also the topology design and sizing. As I was telling, the rail mesh, right? But you can actually tell us any topology on that. And the fifth one is the power cooling PUE. Right now we are running at 1.5. B300, if you look at B300, each node is like 14 to 15 kilowatt of power is going to use. And as Zay was actually telling, if you go with Grace Black, you have to go with NVL 72 or NVL 144. There are only 2 options of it. If you go with 144 is not okay. 144 is not. So, but eventually, if it comes like if let's take NVL 72, NVL 72, you will be end up like what? Almost like 100 kilowatts plus like 150 kilowatts.
132 kilowatts a rack.
Yeah, exactly that number. So 132 kilowatts per rack is what is consuming. So right now we are at 1.5. When B300 is actually hitting, we will go for the water cool and everything. So I think we are looking at the PUE will be actually going down when in our case. But if you actually do it by yourself, I think that PUE you need to see like how exactly you will manage it. That's my whole point. So the sixth point is SRE and operational. So whatever the problems that we discussed so far, everything is a one full-time job. Each one, for example, GPU refresh or RDMA fine tuning, it's not like one single task that I do it across. It's each full-time job that my team is doing 24/7, and they actually be ready with the any events are happening. For example, we are actually saying ballpark figure for any 1,000 GPU clusters deployment, 5 to 10 hardware events we are actually saying. Not necessarily that GPU or our node itself is down. I mean to say the power consumption is high, or the latency we are actually seeing for this network latency we are seeing for this particular node is actually high. So there are some of the hardware events we are actually seeing, and we have a SRE team which is working on 24/7 monitoring with the DCGM monitoring for the NVIDIA. We have Prometheus, Grafana dashboards sitting there, monitor it and get it done, solve it for you, right? So yeah, the bottom line is you focus on research and model. We focus on the platforms that they run. We make them run. So that's the model I actually wanted to bring in. So if not, any questions? Yeah.
So you were saying that storage is someplace else and the GPUs are someplace else.
Yeah.
So say I am reading, I have my data will always be
right.
Needs to go to the GPU.
Right.
Sorry. And you're saying that the band, like the transfer speed is around
200 Gbps.
200 Gbps.
Yeah.
How does that compare with, say, a typical, say H100, which has a PCIe link or something?
So,
see, HBM is obviously the fastest. Local hard drive is obviously the next fastest.
Okay.
By far. Unfortunately, you can't put infinite data in your local, and you cannot share your local among all your nodes. Right?
No, I just want to know how slow it would be comparatively.
You know how much
local NVMe right now we are actually seeing 800 IO, but GPPS I don't exactly know, but it's 800 IO as per our benchmark.
It's about 4 times faster.
4 times. Okay.
I actually copied onto 6 nodes and.
Right.
No, that's fine. I just an approximate number just to have the conversation. So basically, I'm guessing what would happen is the storage will get onto the server, which goes to the HBM, and the compute will happen. Right?
No. So
or it will directly go to the edge.
So HBM once, whatever model that you actually wanted to actually run it, you need that entire HBM should be there first.
No. First, are you training or are you fine tuning or are you inferencing?
Doing some computations.
Okay. So if you're inferencing, you don't need the storage.
Yeah.
You'll use the storage only for lookups.
Yes.
It's actually not worth putting it on high performance storage. Just put it on an NFS because you're not going to need that kind of bandwidth if you're inferencing.
Okay.
Right? If you're fine tuning, what are you doing? You've got a model that's sitting inside HBM. You've got some KVKation data and all of that sitting in the rest of the HBM. You're pulling a whole bunch of data and pre-caching it inside memory from the storage across 10, 12, 14 nodes, whatever that is. And that data that is churning in and out of HBM is reading and writing from memory rather than thing. And your storage is essentially filling up the memory during compute cycles, right? Even in that case, your requirement of storage bandwidth, I've rarely seen it cross about 0.2 Gbps per node. Gigabits per second, gigabytes per second.
No,
capital B, right? When you're training, right, you are essentially what training is essentially you're shoving data into the thing. So you're in a train run, most of your HBM is actually data, correct? And you're refreshing that data continuously. Plus, you have to transfer this data to multiple nodes, otherwise it doesn't have consistency. Because of which the storage throughput becomes fairly important. Even then, 0.8 gigabytes per node is considered high. I'm talking read. 0.8 read, 0.5 write is considered high. One read, 0.7 write is considered really high. You'll do one read, 0.7 write when you are doing video models or some voice models, especially smaller voice models. You'll get to that kind of bandwidth. If you're doing text models, you won't come anywhere close, right? When you set up storage, there are two things that matter: bandwidth and space.
Sure.
Right? Space is easy. It's so many GB thing. If you want more bandwidth than what that space officially allows, the cost of that bandwidth is really expensive for me because I need to go put. I'm essentially delivering it out of memory and pre-caching it.
Yeah.
Right?
So there is one part of it which becomes pretty important for us is checkpointing, because we are not
Checkpointing
just
is always
interested in
local.
training for
Checkpoint is always local. Never checkpoint on PFS. It's a waste.
right? No, but we will need to. So basically, when we are doing a training, we never really do training for training's sake, right? What we wanted to do is do an analysis on those individual at the level of epoch or something of that sort.
Yeah.
So for that, they should be stored somewhere, right?
Yeah, that's
Correct.
checkpointing.
The checkpoint
Yeah.
you store on the local NVMe.
Yeah, but that's not going to be persist. I mean, at
Yeah,
some point of time, it
NVMe
has to go back to this.
NVMe is persistent.
No, I mean, at some point of time, say like the training run happens, those checkpoints will have to go
You
back.
never need the checkpoints. The checkpoints are redundant after some cycles.
No, they are the most important ones, because we will be reading those checkpoints post the training cycle to check, say, did the parameters drift.
Yeah, then you'll have to do dumps. You'll have to physically do
checkpointing
dumps into your
usually-
PFS.
Yeah.
Right?
Checkpointing usually go to the
That's
PFS.
more a research. I understand.
I mean, of course, that's our.
I understand that. You'll have to schedule dumps.
Okay.
It is possible. You'll have to schedule dumps because the local NVMe is typically going to run
To the storage. I think when you see
to dump, you'll dump
the
onto the storage, onto the PFS. But both NVMe and PFS are persistent. The PFS is on a RAID group, so you losing a disk doesn't lose you data. Local NVMe is local NVMe. It's one disk. Lose disk, data gone. But lose disk, data gone. Reschedule the job, run it again in.
no, not so NVMe. It's not just when you lose disk. Say we close the session down and start a new session, we won't be able to access.
You won't lose scratch at that time. You won't lose checkpoints at those times. You can set it as retain persistency of checkpoint. What's the command for it?
I don't know.
Sorry, I just lost the
I
context.
remember.
Okay.
I've done it.
Yeah.
There is a
Okay.
command to retain persistency.
Okay, so
you go set. It's in the job schedule. There's a
Okay.
operator that does it.
which will
That retains persistency of checkpoint.
okay,
You
and
can,
then say
and you can say that revolve and hold 20 checkpoints, 12 checkpoints.
okay.
After that 12 checkpoints, the 13 checkpoint will get deleted to write the next one.
But we might need around 200 checkpoints. That's not something which is stored on the NVMe.
I
Right?
think
200 checkpoints a lot.
I know, but I mean, again, our whole research is analyzing those how it's.
Yeah. So if you need 200 checkpoints, you can say that okay, after every 50, 20, 30 checkpoints, you'll do a dump and refresh and purge all checkpoints.
Okay. So something like that we need to manage.
Yeah, you'll have to figure out how to do it.
So yeah,
I
then
don't know yet. I
But-
don't know because
but
I've
your
never
No,
done
no,
it.
that's fine. But my question is on the other side. So when this is happening, is compute getting affected?
Yes.
Right? So which means all of this process will actually stop the compute.
It won't stop it, it'll slow it down.
I mean, slow it down in the sense it stops for
See,
a
it's not using
milliseconds. or so.
GPU.
yeah.
See, here's the thing. When I say slow it down, I'm talking of 1%, 0.5%. Because any file system activity is run by CPU and RAM,
Mhm.
right?
Yeah, there's a logic.
GPU activity is not affected by that. But the GPU is pulling from your PFS to RAM to feed into HBM,
Yes.
you're going to use some of that memory.
Yeah, but
Yes.
still,
So yes, you are going to lose 2-3% of performance, but it'll be very small loss in performance. In fact,
if your question
honestly,
is,
unless what model are you training? Give me a
So I think we checked
text,
out
text, image,
image,
text, image.
images, classification, maybe vision transformer.
I'm not. I'd be surprised if the loss in performance is more than 1%. I'll be surprised, but I've not done it, so don't hold me to it.
Yes,
I don't know.
so,
Right.
but your question, I think question is to rephrase that. Are you asking if there is a CUDA compute is idle when this millisecond or microsecond level of the checkpoint reference or read and writes are happening? Is that your question? What are the
not exactly. I'm more or less thinking that compute will happen very, very fast.
Yeah.
I mean, that part I think
Correct.
I intuitively get. But these memory operations of writing the checkpoint and reading the checkpoint,
Right.
and it should also collect the data and read the data.
So you don't do that. So your checkpoint is still local. You write checkpoint local.
Okay.
After the checkpoint has been written local, you write in the OS, you write a script to go copy this checkpoint back to the PFS.
Okay.
If you do checkpoint to PFS, it'll die.
Right.
Yeah.
So that is what we sort of phased earlier.
Yeah.
If you do checkpoint to PFS, you will die.
Because
With
it's
the
just
performance
200.
will hit the road.
Yeah. So okay. So how do you handle that? You should handle that at the slurm level.
Yeah. So no. So Slurm doesn't do that.
Okay. Okay.
So Slurm will schedule the job.
Uh-huh.
You can tell Slurm how many checkpoints you want to maintain, right? You go to the OS of the node after that and say and write a what you write
It's
a sync.
Simple script
Some
like
bash.
bash script.
Some
Bash
bash
script
script
itself is enough
to
to
every 20 seconds sync this checkpoint volume to thing. If file equal to complete, sync, and after that delete.
Okay.
So otherwise you'll run out of space on your checkpoint flow.
Yes.
You'll have to. But it's possible to write.
Yeah. I mean, I guess so. But
yeah, it's some batch script. That's all. 15 minutes, I'll write it.
Yeah. So if you look at the 20 Gbps of the network bandwidth, if you are asking for what is the storage bytes that you are actually we are actually net we get it, you will get like 15 to.
You can, right? Checkpoint volume is mountable.
It is mountable, but from GPU to if it goes to PFS again, it will add the latency. Instead, it is
The checkpoint volume is mountable.
You're saying directly the PF itself with
when it's running Linux FF or what you call ext4,
okay.
ext3, ext4.
Right.
But once ext3 is mounted to the Slurm header, how will you mount it to another volume? For copy.
Yeah.
Okay, I'll come back to you.
I'll come back.
I don't know.
Yeah, sure. Because I think this is a place where we had an issue earlier. So.
I don't know. I'll come back.
So, but net, if to give you the 200 Gbps of the speed, you can convert that into 15 to 20 gigabytes per second, which means if your checkpoint volume is actually 15 GB that you are actually saving for, let's say every 1 minute, let's assume, you should be able to comfortably save it because you can transfer 15 GB per second, right? So per minute you can multiply it by 16 and then you have like enough space in terms of the volume copy. But if you do it from the GPU, I think as Zay mentioned, there will be latency. We do that. Okay.
Yeah. By the way, I've not seen anybody checkpoint here. Please don't. Find a way around.
Yeah.
Then it's okay, I'll come back. I need one more to pair up, see whether I can mount it. Give me 2 days that day.
So yeah, we can have a logical.
Stop now. Yes. Okay. So yes, you have already made the announcement.
Yeah.
You guys have to take it.
Yeah, I have.
Oh. But maybe we can take a 10-15 minutes. We can come back.
Yeah.
Yes.
What do I do? I'll just leave it as it is. This recording keeps going.
The recording is going.
But I forgot the things